Good morning, good afternoon, everyone. Thank you for joining the IEEE EMBS webinar series on the frontiers of biomedical imaging and analysis. My name is Pingkun Yan. I'm the Associate Professor of Biomedical Engineering at the Rensselaer Polytechnic Institute. I'm co-hosting this webinar with Doctors Hamed Kaskan, Marlene DeBruni, Maria Slingraju. We are all part of IEEE BIP Technical Committee. So today it is our great pleasure to have Dr. Holger Roth to be our guest speaker. Dr. Roth is a senior applied research scientist at NVIDIA, focusing on deep learning for medical imaging. He has been working closely with clinicians and academics over the past several years to develop deep learning-based medical image computing and computer-aided detection models for radiological applications. So he is the associate editor for IEEE TMI, Transactions on Medical Imaging, the top journal in our field. In 2018, he was awarded the Mikai Young Scientist Publication Impact Award. This Impact Award has actually been evaluated over the several years since the publication to see how large is the impact of the paper. So it's not just for the single year best paper award, but actually impact over the years. So very prestigious. Dr. Roth has been a leader of federated learning in the medical image analysis. So today he will speak about his research on advanced techniques for collaborative development of AI models for medical imaging. So without further ado, let's welcome our speaker. Thank you.
Thank you very much for the very kind introduction, Pinkham. Okay, so I want to take this opportunity to talk a little bit about the techniques that we developed for so-called collaborative medical imaging. See, okay. So one of the main challenges in developing AI models for medical imaging is the data, right? There are challenges around data preparation. There are challenges about the diversity of the data. How can you gather enough data for such that you can build AI models that can generalize well in practice, right, when you actually deploy them. At the same time, in order to build these large data sets, you have to take data privacy, in particular, patient privacy and data governance into account and conform to regulations, right? So this is actually a relatively large burden that's specific to, not only specific to medical imaging, but somewhat enhanced in healthcare. You have to take this privacy constraint into account in order to build your large data sets that can be used to develop robust AI models. So one solution that can help with this is federated learning. In this scenario, we don't have to share data in a kind of in a centralized database, but each data owner can keep governance of the data. The data can stay on site, but let's say each site being a hospital or a research institute, they can still collaborate to train more robust AI models by using federated learning techniques, where you would have like a central parameter server that learns a global model, and each of the data owners is receiving this global model and then trains it on their own data and shares some information, some updates of that model with the central server. In that way, sites or hospitals can keep governance of their data while still collaborating to build these more robust AI models. There are different scenarios of this, in particular with regard to how data is partitioned. So in the I would say the most common scenario is maybe the horizontal federated learning, where or homogeneous federated learning, where data is split by example. So each hospital site has like the same kind of data and labels most of the time, so the same features, and same kind of labels, but different patient populations. Whereas in the vertical data partitioning scenario, also called heterogeneous federated learning, you have actually each site maybe having a certain set of features that correspond to the same set of patients across several hospitals or sites. So like an example of this could be one site has imaging data of a certain patient, while another site, like the pharmacy, has blood test results, or there's the electronic health record at a different site. And so in a vertical partitioned federated learning scenario, you could still train models that can combine these different sources of information. And there are applications of federated transfer learning. So you can basically take models from one side and fine tune them on another side. Or there can be all kind of extensions of these schemas, right? Hybrid approaches of multitask federated learning. One other important aspect of this federated learning infrastructure is federated evaluation. So once you have built this consortium or this collaboration of hospitals, right, you can use that to also easily evaluate your models on a large and diverse set of data sets. So that will also, I think, play an important role with respect to regulatory approval of AI models. I want to highlight one of the main differences to other industries in healthcare applications of federated learning. As you might know, federated learning came from the mobile device sector, where you typically have tens of thousands or even millions of users on small, low compute resource devices, mobile phones, and you want to use all that data in a privacy-preserving manner to train more robust AI models. We don't really see this application so much in healthcare yet, but of course there could be applications of related to wearable devices and things like that. But what we typically have been working on, at least, is the so-called cross-silo scenario, where each client or each participant in the federated learning is a larger scale institute with a larger amount of data and also compute resources. So you're typically talking about tens to hundreds of different hospital sites, and there are also some considerations that influence how you build your federated learning framework, right? Here in this scenario, you can assume that each research institute or hospital has relatively stable internet connections and a good amount of compute resources like GPU memory. While some of these assumptions, of course, are not true in the mobile phone or cross-device scenario. If you're interested in how federated learning can apply to medical imaging, we've written this paper in digital medicine, which goes into the different benefits for various stakeholders in your healthcare applications. As I said, currently a lot of the research studies around AI models in medical imaging and healthcare don't do large-scale evaluation of their models. So we know that AI models work well in the local, very controlled environments, right? But once you move them to the real world, you can typically see an impact on the performance due to domain shifts and different patient populations, different acquisition protocols. So as I said earlier, federated learning can be a way to build up this infrastructure to do large-scale evaluation of these models. So, excuse me. Next, I would like to introduce some of the use cases that we at NVIDIA have been working on in particular. We started kind of our venture into federated learning in 2019 with some study on brain tumor segmentation in a federated learning scenario. This was simulated, but looking into some of the privacy aspects by adding differential privacy to the model exchange and showing how that affects the model performance. And then we did a couple of real-world studies. First, in 2020, this was published in 2020 for breast density mammography estimation, where we had several sites in North America and also in Brazil doing a real-world federated learning implementation, right? So these were physically separate hospitals that were training a model together. We then also worked on prostate segmentation between 3 sites in the US. We did some pancreas segmentation study in Asia between National Taiwan University and Nagoya University in Japan. And most recently, we did our largest study so far with 20 collaborators around the globe for predicting the oxygen needs for patients arriving in the ER with symptoms of COVID-19. So I will go into some of these projects in more detail. For the pancreas segmentation task, this just had 2 clients that were working together. But the interesting aspect here is that one client only had healthy cases, so they only would have labels for background and the pancreas, while the other client had cases of pancreatic tumors, so they had labels for background, pancreas, and tumor. So now you can see one of these main generalization issues of AI models. If a model is only trained on cases with pancreas and tumor, it is actually likely to also produce false positive tumor detections, which of course you don't want to have in this healthy patient. So in contrast, the model that is trained using federated averaging, right, so this is our so-called global model, is more robust and it can correctly, or it doesn't produce a false positive tumor segmentation on this healthy patient. And if you look at this the other way around, right, here is the model that was only trained on healthy pancreas applied to the other client's data set. You can see, of course, this model has no concept of a tumor, so it's missing this large tumor completely, while the global model is doing a reasonable job in detecting the tumor region. So this shows the benefit that these kind of clients with even diverse data sets, like different types of annotations, can work together to train more powerful AI models. Now, this Nature Medicine study on involving 20 global sites was published last year. You can see, of course, from the author list that this has been a large collaboration effort. A lot of people had to contribute in order to make this work. And in order to do this in the real world, of course, you have to take different considerations into account, like easy deployment of the federated learning toolkit on the different hospital sites. So we have a way of provisioning these so-called startup kits for each hospital. And in that way, we can also add an authorization certificate that can make sure that only clients that are allowed to talk to the server can participate in this study. And then we have an admin console where a researcher can interactively change configurations, training parameters, look at results in order to, do hyperparameter tuning and try out different models in order to arrive at a good final model. So the model that we arrived at was this multimodality model. It's taking both chest X-ray and EHR data into account to predict the need for oxygen treatment when a patient arrives in the ER with symptoms of COVID. So we actually trained two models, one for predicting for the oxygen need in 24 hours and one for 72 hours. And if you look at the data distribution across different sites, you can see that we had, in terms of the amount of data, we had quite some variation. Some large clients contributed, of course, very important information, and smaller clients also valuable data sets. And if you look at the chest X-ray intensity distributions, this was also quite varied due to the real world scenario here, right? We have different patient populations, different scanner equipment, different protocols on these different sites. Also, the patient's age population was kind of what you expect for a COVID risk population. But one thing to highlight here is that we also had a pediatric hospital where you can see that the patient age was actually much lower. So that also contributed to the diversity of data that is beneficial for the model. Then here we see the local performance of each hospital training their own model on their own data. This is ordered by size. So the largest, number one would be the hospital with the largest amount of data. So you can see that they can train a reasonable model with like a AUC around 90, but even they get a benefit from using the global model, right, from that was trained in the federated learning fashion. Of course, some of the smaller clients, they have like a pretty much a random prediction, even on their own test data, but they get a huge boost in performance by using federated learning. And then here on the lower graph, we also show the generalizability with respect to the number of images that each site had. Again, so generalizability here means like how well does your model perform on the other clients' data. So you can see again, small sites with small amount of data, they don't get a good performance, but even the largest site gets a boost when using the FL model, right? So we can say that the generalizability improved by 38% when all clients train together. Here we can also compare a couple of local models that were trained on mid-sized clients, but applied to a client from a different part of the world, so a completely different ethnicity. Here it was like 5 US models from Boston applied to one client with a smaller data set in Asia. And again, you can see that compared to the local model, the 5 models from Boston actually perform better, but they are still outperformed by the FL model. So again, this is pointing out the better generalizability or better robustness of these global models. Here, just to mention, these are different cutoff values for the oxygen prediction. If you're interested, we actually released these models, as I said, for 24 hours and 72 hours on our NGC platform. And when we tested this model externally on a data set that was not used by any of or was not belonging to any of the clients that were participating in development of the model, we achieved a sensitivity of 95% and a specificity of 88%. Okay, so now I would like to go into more detail about some of the FL algorithms that are currently state of the art, and also some that we developed in our team. Some of the main challenges on the algorithmic design are these basically heterogeneity of data across different clients. Right now, not all data is just randomly in one place, and you can randomly shuffle data. Now we have this physical barrier between different data sets. They all have their different distributions, so that is typically called a non-IID setting. So there have been several works that try to address this by adding different regularizations or loss functions, or changing some of the aggregation protocols when you do the update of the global model. So those algorithmic developments can be useful to address these non-ID issue of the data. On the other hand, there are also challenges around the hardware. There might be hospitals that have stronger GPU clusters compared to others, right? So you have this potentially straggler problems where one client is waiting for other or where one client causes other clients to wait because it's slower. In that case, there's potential here for research into asynchronous ways of aggregating the models. Here, just an illustration of how non-IID-ness or heterogeneity looks like in medical imaging for different applications. So you can have different types of non-IID-ness. Could be label unbalance, or features unbalance, or even just the quantity of data across different sites. If you remember the slide I showed from the COVID study, we could see that in both the quantity unbalance of different clients, but also things like the intensity distributions look quite different across different sites. So you will always run into this issue in real world application of federated learning. Here's another example of this, one of the studies I mentioned earlier for mammography data, where we trained a model that estimates the breast density. Here you can kind of see all three kinds of non-IID being represented here, right? You have the feature distributions look different, also appearance of the images across different sites, but you also see label distributions, like sometimes differences in the label distributions, like this client is kind of an outlier because it doesn't have any of, has nearly no examples of this red class. And then the quantitative differences in dataset sizes. So these things need to be taken account for applying federated learning in real world scenarios. Just to back up a little bit on how the federated learning actually works. In most practical applications, we use the federated averaging. It's maybe still consider at least a very strong baseline to start with. And the way this works is that a federated server initializes a model, then sends that model to each site, each hospital. They train on their local data, keep the data on site, and then send a weight update to the server. The server does some, in the simplest case, weighted aggregation, weighted sum of these updates, and adds it to the previous global model, and then this is iterated, right? And if you want to keep the privacy in mind. I mean, there's a theoretical risk that these updates might leak some private information, which I will actually talk about later on. You can add additional measures like differential privacy or encryption in order to avoid leaking any information. So now these standard extensions of federated averaging have been proposed, like FedProx, which adds another regularization term to the local training to avoid the local model to drift away from the global model too much. This kind of trying to reduce this so-called client drift problem. There are other algorithms like FedNova, which add additional computation to the update step, or Scaffold, which has this introduces these control terms that are added both in the local training and on the server side update. I also want to mention that there are, of course, applications of semi-supervised learning. So you could combine data sets where only a subset of the clients has annotations, but you can still learn from clients that only have images, right, in an unsupervised or self-supervised way. In that way, we can still achieve better performance by using by combining these different types of data in a federated learning model. So our team has been thinking about how to address Unity problem, and currently like two lines of thoughts. One is personalization. In that way, we can train models that can be more adapted towards the local client data populations. And another line of work that we find quite promising is to look into more efficient hyperparameter tuning, because all these parameters that you have in different FL algorithms, right, they kind of come on top of your typical set of deep learning hyperparameters that you already have anyway, like augmentation or different network structures. So you end up with even more hyperparameters in the FL setting. So looking at ways on how to automatically find the best hyperparameters is going to be important. So on the personalization, this is kind of a well-known limitation of federated averaging, right? Because each client is training locally on their own data distribution. The models are starting to drift away from the global model, but then you're averaging again by trying to minimize the sum of all participants' clients' loss function. And that might impact the performance of the global model. So for personalized FL, we try to address this issue by training models that can perform well on the individual clients, but still taking or gaining the benefits from other clients while by using some sort of less stringent federated learning approach. In the simplest case, this personalization can be achieved by just fine-tuning your global model on each client's data, but you're losing, or you have the risk there that you're losing generalizability, right? Because now you're taking the global model, you're fine-tuning on your local data, and you might improve the performance on your local test set, but you have the risk of having a lower performance when you then apply this model to other sites or in clinical practice. Of course, there are ways of dealing with that, also like learning without forgetting, or elastic weight consolidation comes into mind, which might play a role here. We also looked into personalization via actual neural architecture search, so finding the best model architectures for each client can help boost the performance on each side. So this is one approach, combining the model architecture search with federated learning, or we can have personalization via training a model selection network. So in this case, for each side, we train a personalized model, but then on top of that, we also train a selector that can choose, depending on the test image, which model to execute. In that way, you're basically training an ensemble of different models, so-called supermodel in this case. And the selector can actually, the model selector is kind of a lightweight model that can choose the most appropriate model to give you the best performance at test time. And this work was recently accepted as CVPR 2022. Excuse me. If we compare this with several baselines, we can see that the supermodel approach can add a lot of performance on the overall test scores by having these more client-specific models. Sometimes even outperforming the centralized model, right? Because now you have a supermodel that's more powerful, has like more parameters compared to one model trained on the entire data set. Okay, on the so-called auto machine learning, or auto federated learning, as we call it here, side, we have done several works. One is to train these aggregation weights that we have in federated learning in a data-driven way. So rather, typically these aggregation weights that are used to update a global model are based on heuristics, like the local data set size is typically what people use. So they weight clients with more data higher. But of course, we know that more data doesn't necessarily tell you that it's more relevant data to your AI model performance. So by learning these aggregation weights during the federated learning, here we can see how the weight is being learned as we go through the several rounds of federated learning training. We can achieve a higher performance compared to the federated averaging baseline. Excuse me. Here are some qualitative results. We can see that the federated averaging baseline model still performs, produces some outlier detections here, while the tuned model using the auto-federated averaging achieves a more robust segmentation of these more challenging cases. More recently, then we looked into ways of tuning more of the parameters that you need in federated learning efficiently. So here we use an online reinforcement learning algorithm that can, again, as you train your model using federated learning, you can tune the parameters to arrive at a performing model. Excuse me, got a little bit of a cold here. So here we basically also take hyperparameters like the aggregation weights are being learned. Here this is a CIFAR 10 example. So we have, we're using 8 clients, I think. Yeah. And you can see how this automated Reinforcement learning can improve the performance compared to the baselines. Here we also artificially generate a heterogeneous data split by sampling the CIFAR-10 dataset from Dirichlet distribution, and in that way you can see, the clients get like different number of images, different amounts of unique labels to simulate this non-ID issue. And then if you run this on like real world data, like real multi-institutional medical imaging data, we can actually tune different parameters like the local number of iterations, local learning rate for the clients, the aggregation weights, and then here we also use a server-side learning rate. You can imagine that instead of just averaging updates and adding that to the global model, you can actually also use a server-side optimizer that can be an adaptive optimizer, right? With a learning rate. In that way, you also achieve better performance. And then we can look at the importance of different hyperparameters as they change during the training, like how much benefit in terms of the model performance was the change of the hyperparameter giving you. In that way, we can see that the server learning rate is actually quite important, but also aggregation rates and the local learning rate plays a big role. So if you can tune these automatically, you save a lot on your manual experimentation time. Again, here we use this multi-institution pancreas segmentation data set in CT and achieve better performance. Here the reinforcement agent is a multi-layer perceptron that kind of uses deep reinforcement learning, which gave us the best performance here. If you're interested in AutoML in general, our team has also published several works over the recent years in this field, in particular recently on neural architecture search. Have some state-of-the-art models that each year they basically improved the leaderboard on the medical segmentation decathlon challenge. Okay, so for the next part, I'm concentrating on the security and privacy aspects. As I said earlier, that federated learning gives you the possibility to train AI models in a privacy-preserving way, right? But you're still exchanging information about local data in forms of model updates. So the question is if somebody can maybe invert your models to reconstruct local data or invert the gradients, or even using some generative models in order to learn something about your data distribution. So these kind of scenarios are somewhat theoretical at the moment, but I would say they are possible. So we have to take that into consideration. In this work, we assume that the server cannot be trusted. So the server is compromised by a malicious actor that is observing the gradients that are being sent from each hospital, right? So the question is like how much about the underlying data can this malicious actor reconstruct by just observing the current state of the global model and the model updates. Here we use a chest X-ray classification example. This is again COVID versus non-COVID. We show that some baseline reconstruction methods actually don't work well if your model uses batch normalization layers. If each client is training the model and updating the batch norm statistics, then you have to take that into account. By here we define a particular batch normalization norm loss that can be helpful for the reconstruction. And then here we show also that you need to have access to the global current state of the global model as the attacker. So you can match basically the updates with what the updates were with respect to. In that way, we can get this level of reconstructions if the client is sending gradients based on just one image, right? This is the big caveat. You can see even in that scenario, which is, as you can imagine, quite unsecure, you can get a lot of information about the image, but things like the actual text in the image, like here we artificially inserted a random name to see if we can reconstruct it, but that at least with the current state of the art of text, it was not possible. And then once you start looking into more realistic scenarios where clients actually train with a batch size larger than one, we can see that the reconstruction quality goes down quite drastically. Also, what you do normally in federated averaging is that you train for several iterations locally before sending the update. You can see as you add more iterations over different images, we see the reconstruction quality go down dramatically. And this is just because the attack cannot estimate all images that were used in this local training correctly. Another common way of preventing this type of attack risk is to add differential privacy mechanisms into your model training. So here we add Gaussian different privacy. So basically adding Gaussian noise to the model updates that are being sent to the server, like before they leave the client. In that way, you can see with more amounts of noise, the attack becomes less successful, or basically unfeasible. However, I should say that Gaussian noise added to the model gradients, of course, impacts also the model accuracy. So this is this gray line here. We can see that the testing accuracy goes down. But even for a client which is sending updates based on one image, we can reduce the data leakage. Here we come up with a relative data leakage value that basically indicates that if this value is below 0, then the reconstruction looks basically closer to Gaussian noise than or the attack prior that we use here than to the original image. In that way, we have kind of a way we can compare different clients. We can see that these other clients 1 to 8, were actually all having more than one image, and none of them has been really leaking information in this using this measurement. So some of the conclusions here is that, you know, what is insecure, like you shouldn't, like if you only have very small data sets, then you have to be more careful, maybe add more differential privacy noise, or do an encryption, like homomorphic encryption. We have also a solution for that. And if you have small number of local iterations and small batch sizes, this is all making it more likely that an attacker can reconstruct data. So the recommendation is to use larger data sets and send updates from large amount of iterations and use large batch sizes. So all of these makes it pretty impractical for attacker to reconstruct the original images. For this year's CVPR, we also worked on showing how vision transformers are in particular vulnerable to this type of inversion attacks. So here, because the architecture actually changes in comparison to convolutional neural networks, you can see that somewhat more data is leaked. Right here, for example, in this lower image, we can see a ResNet 50 being inverted. Not quite right, but for the grad read, we can actually inverted pretty much exactly, and that's because of the local batch embeddings that are being used in the transformer models. So I think this is just highlighting that there needs to be more research into how different model architectures can impact privacy, and maybe we need to be aware of these potential issues. So in conclusion, federated learning security is somewhat multi-layered. You have to take different considerations into account, like user identity structure, using public key infrastructure, for example, to make sure that only people with authorization can actually join your effort. Also, all the communication channels should be encrypted, of course. We typically use SSL encryption as the state-of-the-art protocol there. And then even with those measurements taken into account, you still risk leaking some information from the algorithmic procedures itself. So you can add differential privacy or homomorphic encryption or secure multi-party computation to make sure that your algorithm itself is also safe. Again, I was mentioning earlier that we do have examples of homomorphic encryption that can be used for FL in some of our NVIDIA solutions. I will actually be talking about software solutions in the last part of the talk, and differential privacy has also been implemented. So yes, on the software tools from NVIDIA side, we just last year we open sourced our solution that was used for running all these real-world federated learning studies for medical imaging in an SDK called NVIDIA Flare. That stands for Federated Learning Application Runtime Environment. Right, so it's an open source toolkit that can be used in different industries. It's actually very agnostic to the underlying machine learning algorithm that you use. It's kind of a more general distributed compute platform in my opinion. So you can implement all kinds of distributed workflows. There's a set of algorithms that we implemented based off state-of-the-art literature, going from this vanilla federated averaging, kind of the gold standard in this case, to more advanced algorithms like fedprox, fedopt, or different ways of communication. Rather than averaging in the central place, you can actually also do a cyclic weight transfer and pass these models around, and you can do personalization. And as I said earlier, there are solutions for differential privacy and homomorphic encryption. I'll skip through this. It's just showing that you can run different simulation settings with NVFlare to compare the performance of different algorithms. Here on Cipher 10, we can see that by using these more complex algorithms like fedopt or scaffold, we can achieve better performance compared to the baseline at averaging. And then we also have medical image specific examples like brain tumor segmentation using differential privacy or prostate segmentation. A lot of the medical imaging based solutions in federated learning, at least in NVFlare, they're based on Monai, which is another effort that's currently ongoing in the open source community, where NVIDIA is also heavily involved in the development, but together with several universities and research centers around the globe. So really a community effort to build domain-specific solutions for medical imaging. So things like 3D transformations that are not typically in your standard deep learning frameworks implemented here and tested and made production ready, basically, by using GPU optimized code. So in this, there are many tutorials for you to get started. It's pretty easy learning curve, I would say, to get started with this library. And as part of the Monai effort, we also have a federated learning specific working group led by Jayashri Kalpathy-Kramer, Daniel Rubin, and myself, where we mainly focus on building more federated learning examples with Monai, build some reusable components, and we're also starting to talk about standardization so that different federated learning frameworks might be able to talk to each other. And if you're interested in this topic, please also have a look at a survey that we have ongoing. You can. It would be nice to have your opinions gathered in this survey. Currently, we have several examples using different FL frameworks, like the NVFlair from NVIDIA that I described earlier. There's OpenFL from Intel and Substra from Okin, which you can have a look. Again, if you're more interested in this federated learning topic, there's a workshop that we have now been organizing for the last 3 years. So this MICAI workshop will happen in September later this year on distributed, collaborative, and federated learning. I forgot to put a deadline here, but if you're interested to submit your paper, that's going to be June 25th. And with that, I would like to thank you for your attention.
Thank you, Holger, for the very nice presentation. Covers quite a range of applications and algorithms. Also, it includes a lot of excellent publications, a lot of information to absorb. Very nice. Now we can actually open the floor to the audience for questions. While actually the warm up, I can start with a question. So I saw that actually in your application, basically the software tools, you use multiple tools. In the early part of the talk, a lot of them are on the Clara, and then later on you mentioned the NVFlair, and also now there's more like open specialized for medical imaging, the Monai. So how does Monai actually integrate into those applications, into those platforms? What's the relationship between NVFlair and Clara?
Yeah, so there's of course a kind of a historical perspective to this, right? For the last couple of years at NVIDIA, we have been developing the Clara SDKs, where our first solution for federated learning was like built in, but closed source. So we use that for that library within Clara we used for running some of these FL studies that I described. And then last year we kind of decided to make that library open source so more people can benefit from it. So that has been done. That library for federated learning has been called NVFlair. So that's now under Apache 2 license. So it's ready to use in many different applications. On the Monai side, I mean, that effort has been ongoing for a little bit longer, also towards the academic community to build like an open source platform. You know, I think at the time there have been a couple of efforts into building deep learning based solutions specifically for medical imaging, but kind of competing efforts. And so a lot of people from the academia thought that actually why not bring those different efforts together into one common consortium, which then resulted in a Monai toolkit. And there are definitely actually several kind of sub projects like the Monai training, the Monai label is like annotation tools, which are very interesting, and Monai deploy, which actually is also very similar in spirit to some of the toolkits that we previously developed at NVIDIA around Clara Deploy, right? So a lot of the developers from Clara Deploy are now working on Monai Deploy, and the same is true for the training part. We had like the Clara Train SDK. If you look at the latest release, it's actually under the hood. It's all using Monai. Like, so all our functionalities have been migrated to open source and integrated in Monai.
Okay, I
While
see.
Clara is the Dockerized solution that adds some kind of configurable and ready to use training plans and model files to it, which is all built around Monai, actually.
Okay.
So
So, for
it's a
example,
bit of a complicated story, but
all
sorry.
right, yeah, got you. So let's say if actually for students who wants to actually do federated learning, medical imaging, so maybe you recommend the best entry point would be NVFlare plus Monai.
Yeah, I mean that if you now look at the NVFlare repository and the examples, you will see several examples of using NVFlare with Monai, and that it's completely open source, so it's you know, it's the easiest way to get started.
Okay, cool. Yeah, we got a couple of questions from the audience. The first one from Abbas. For federated learning security, you mentioned increasing the batch size to combat attacks. Any range do you recommend?
Yeah, so in our experience, anything that was kind of your reasonable batch size that you would use for deep learning, like, you know, starting from like 32, was already showing that the attack is very feasible in some way, in some sense, right? It was not showing to leak a lot of information. So we like, unfortunately, this the exact value I cannot tell you, because this is kind of task dependent, right? So for different tasks, you imagine that there might be images that are somehow more represented in the gradients, even if you have a larger batch size. So you still have to be careful that you're not leaking information there. So what we actually propose in this paper is to come up with these quantifiable metrics that you could apply to, at least in a simulated setting. You could measure the data leakage and then find the best parameters for your task. Down the line, we can even think of this running on the clients, right, and kind of giving you a holding up the sending of gradients to the server if too much information was leaked.
Mm-hmm. Okay, great. So next question, the Dr. Xiang Xu actually posting the Q&A. So thanks for the impressive presentation and learn a lot. He has a question regarding the security. Is that allowed to transfer the locally extracted features, maybe a part of feature, to the server in a federated learning system?
Yeah, people do this in so-called split learning, which is a kind of a variation of federated learning. You could actually split your forward and backward paths of the model by combining features from different sides. So that's especially useful in this kind of vertical partitioned scenario, where, you know, different clients have different features of the same patient or user, and you need to have some kind of deep learning model architecture that can combine these features. So you have to fuse them on the feature level. Of course, that adds a lot of more security risks to your algorithm.
Yeah.
So it might need to be done completely using encryption. So currently, we don't have an example in NVFlare for doing this, but there are some frameworks I'm aware of that do this for non-deep learning applications, and they basically do everything using secure multi-party computation or homomorphic encryption in order to get around these issues with sharing activations.
Okay, cool. Thanks. Next question from Xiaoyin Xu. Excellent presentation. Question is, in federated learning, will the local models eventually converge to the same model? If so, is that a good thing or undesirable from the perspective of federated learning?
I mean, if you have a learning rate decay built in, then that would be true. Like at some point, clients will just take the last global model and then not fine tune anymore on their local data. But let's say the learning rate is constant, and of course, then you will always have a client drift, which is due to the non-IID setting of your data.
Yeah, regarding the non-IID data, we recently also did some work on this. So if the data set really very different, heterogeneous, like you mentioned, then actually each local model may converge to a very different place. When you are using the Fed average to combine the models, the global model may be suboptimal.
Exactly, that's exactly the point I was trying to make when talking about the personalization.
Mm-hmm.
So, of course, we in a lot of scenarios we would like to have only one final model, right? That is generalizable across the board, works well on each client, and then also on unseen data. But with the federated averaging, that is hard to do if you have this non-IID issue. Basically, also theoretically, you cannot get around that issue because your optimization has changed, right? So the way we try to tackle it now is with personalization, as I said, and with automated hyperparameter tuning, which can also help you to avoid some of these caveats of non-IIDness.
Yeah, I think actually the paper, your upcoming paper on the CVPR 2022 sounds very interesting using the supermodel. Yeah, we're gonna study that.
Okay, cool.
Yeah, all right. One last question. So from Wei Qinsong, thanks for the wonderful sharing. You mentioned homomorphic encryption for privacy of federated learning. What is the challenge you solve for using the FL federated learning in such an application?
Oh yeah. So homomorphic encryption. Sorry, because of the time constraint, I didn't talk about it in much detail, but the idea is basically that each client is encrypting their updates before sending them to the server, and then there's the server in the homomorphic encryption setting can still do the aggregation of the models in an encrypted space and send back an aggregated result still encrypted, and the clients would then decrypt it, and they get the same result as if the computation was done in clear space or clear text. So this has, of course, a lot of advantages for giving you security guarantees, but it comes with the caveat that the computational burden is really drastically increased. So it's both the encrypted message sizes become much larger, I think by factor 20 or something. I would have, please have a look at a blog post that we posted. I think that shows the numbers. I think it's at least a factor 10. And then the computation time for the overall training was also like 20% larger. The advantage for if you apply it to federated averaging is that you can do the local training still in clear, right? But only this aggregation step that you have to do once in a while is done in the homomorphic encryption. So it's just adding like about 20% overhead on your total training time in some of the examples that we looked at.
Thank you, Holger. Yeah, very nice presentation. Thank you all for attending. So I know there's still actually questions, but we are over time already. So yeah, let's thank our speaker again and concluding the session today.
Yeah,
Thank
please
you.
drop me an email if you have any more questions. Okay. Thank you.
Okay. All right. Thank you. Bye.
Bye.
Take care all.